With the recent releases of cool text-to-image models like OpenAI's DALL-E 2 or text-to-video models like Facebook's Make a Video and Google's Imagine Video, more and more people are interested in the capabilities of what machine learning, or specifically deep learning, can do. For a long time, deep learning in computer vision and games was the hype. Deep learning models could classify images, detect objects, and even segment those. Other deep reinforcement learning models could outperform humans in many games, starting with classical Atari games up to very difficult games such as Go. Currently, the hype has shifted more towards larger language models, probably due to the success of so-called transformer models. So, naturally, some people see those magical models and want to know what they are and how they work. And rightfully so. They are amazing. That said, let's look at what machine learning is. By the end of this video, you will be able to keep up with basic machine learning conversations and have an insight into what happens behind the curtains, which explains a bit of the magic, but doesn't make the performance of those models less impressive and, yes, less magical. The goal of every mathematical model is to have some mathematical representation or equation that describes and approximates a system so that we can feed in some input and have it predict some outcome that would also be produced by the real system. Very abstract, huh? Well, weather predictions, for example, are also based on some model, where you put in some data, for example, the current weather or the weather of the past few days. Then the model does some computation, runs some simulations, and predicts the weather for the next few hours or days. This model is a representation, an approximation of the real system that would generate some outcome. But in this example, this model used to be engineered by humans. Engineers have chosen which features of the world influence the weather and how those interact with each other. But what if we could have a model be created, be learned, by simply looking at the real world and recognizing the patterns by itself? I mean, we as humans do that all the time. That's how we learn, right? But we as humans can only engineer so many features and their interactions. But in theory, it should be possible to mathematically represent pretty much every data distribution. It would just be way too complex for us as humans to come up with or just to grasp. In general, there are two main methods how a human learns. So let's look at one of those, which is to learn by correct examples or by looking at the solutions to a given question. Imagine you see a new animal and you learn its associated name by looking it up somewhere. If you see enough examples of those animals, you can already guess that those are quokkas. But with every confirmation, you will eventually be more confident in your classification. The point is, you usually need to see a few examples of quokkas, and ideally also a few examples of animals that aren't quokkas, but look similar. You need data. So, similar to us, machines need data to learn from. A lot of it. But the good thing, and the reason why deep learning works in the first place in today's time, is that we usually have an abundance of data and a lot of compute power. The fundamental concepts of deep learning and machine learning are nothing new. They date back to the 1950s, I believe. Okay, back to data. We pretty much always need some sort of input to train our models on and then do the predictions on. But this data can have a lot of different form factors like images, audio waves, words, sentences, graphs, sensor data, or just some sort of array or vector that you feed in. But pretty much it can be anything. Nevertheless, the data or the samples that we are trying to learn from have to be representative of the distribution that we are trying to learn. This pretty much just means that we need a lot of different images of quokkas with different lighting, different colors, different angles, and so on. This allows our model to learn all important features a quokka has and then use those to identify one it has never seen before. For example, quokkas have black noses. This little guy doesn't, so that can't be a quokka. First of all, what is a specific example of a mathematical model? I promise I won't go into crazy maths. We have all already seen a mathematical model in school. Remember the basic linear equation y equals a times x plus b? This is a mathematical model. You have an input x, for example 2, and can map or predict that input to some output. In this example, with a equals 1 and b equals 1, y would equal to 3. Now, those letters a and b are the parameters of the equation. They define how the line should look and what output the same input can be mapped to. The goal of pretty much every machine learning model is to learn those parameters that define such an equation in a way that the equation best describes the data distribution from which the data is sampled. In other words, it wants to fit the data well. It hereby starts with some random parameters a and b, and by learning from the data through some math magic, it converges to the correct parameters so that the line fits the data best. I'm going to repeat myself here because this is really the fundamental goal of every machine learning model. Every classical machine learning model like linear regression or support vector machines, up to advanced deep neural networks like convolutional neural networks, graph neural networks, or even transformers, wants to achieve this. They want to learn those parameters that fit the data best. Of course, there is more nuance to it, and they don't only want to fit the data, but they also want to generalize well to be able to predict samples they have never seen before. But again, every model wants to achieve the same goal, but their approach is a bit different. And with more modern neural network architectures, they have a few more parameters they have to tune and learn. The modern large language models are in the billions when it comes to parameters, and in most cases the input size is not only 1x, so 1 or 2-dimensional, but high dimensional. Speaking of nuanced differences, let's look at some key distinctions you have to make when looking at machine learning models. Let's talk about classification versus regression. The case we just looked at would be a regression case. We have some values that are real numbers, and we want to learn the parameters of a model that will return us a real value. You can, for example, think of stock market predictions, where you use the past market's development to learn from and then predict a stock's value in the near future. We can also interpret the data differently. Each data point now consists of two features, x and y, and is associated with a class. Class 1 would be Quokka and class 2 would be not Quokka. We now want to again learn an equation that defines a decision boundary, a line that separates, for example, those two classes. This is then called a classification problem. Another important distinction is whether you have labeled data or don't. In the case of classification, your labels are again the class names, Quokka or not Quokka, and for the regression case, you would have some real numbered value that you expect to get from some input x. This is considered supervised learning. We simply always have an input x and an associated ground truth label y. Unsupervised learning deals with the problem of unlabeled data. It's mostly a clustering task, but we won't go too much into detail here. Theoretically, then there's also semi-supervised learning, but again, too much for this video. Remember how I mentioned that there are mainly two ways how humans learn? Well, the second one is by trial and error in some environment. Inspired by how kids learn to walk, reinforcement learning also tries to implement this trial and error approach. Imagine you drop your character, or in technical terms called agent, into some world or environment. And then you let it perform random actions based on its current observations, so what it sees, also called its state. Go left or go right. At some point your agent hits a wall or just loses a life. This isn't good, so you give the agent a punishment. By constantly performing actions and receiving a punishment or a reward, respectively, then the agent learns which actions are appropriate or good in a certain situation or a certain state. For example, when the agent is located left of a wall, it wouldn't make much sense to go right and crash into the wall or just do nothing. In pretty much all cases, reinforcement learning needs a simulation where the agent can perform random actions. Otherwise, those actions can be pretty dangerous in the real world and also very expensive. By using this simulation, you can teach your agents in a more or less unsupervised fashion to do whatever you want it to do. I know that's very professionally expressed. I said more or less unsupervised because you don't provide a ground truth best action to every state there is in a game, for example, but you have to design a reward function. This reward function that you again design takes in the state or some features of the state and returns some reward or penalty. For example, -1 point for losing a life, but +5 points for winning the game. This seems like a pretty straightforward approach, but to actually get this to work is really tricky, and in practice it requires a lot of specific implementation details, which we won't cover in this video. Congratulations! Machine learning should now not be a huge mystery or some unexplainable magic anymore. That said, it should still be magical. The more you learn about something you knew nothing about, the more the source story behind it reveals itself and you get to know it better and better. Except for diffusion models, so those are still pure magic. Deep learning especially is still in the beginning of its journey to change the world. And I hope by showing you this video I could take away a bit of the fear of the unknown and perhaps even inspire you to dig deeper into this magical world of machine learning. And if that was the case, please don't forget to like. If you want to follow along this journey of learning even more about machine learning and deep learning, please don't forget to hit that subscribe button. And with that said, as always, thank you very much for watching, and I will see you guys in the next one. Bye!